Up until now, we've mostly seen the theoretical aspects of quantum information and quantum computing. So our work was focused mostly on the application side of it, not necessarily those applications in science and mathematics, although those are very important as well, but applications which are of industrial importance. A few topics we need to understand, the two problems we worked on are the preliminaries of the quantum hardware we used and researched for this, and uh, how you go about translating a problem onto the quantum hardware. Uh, the We used D-Wave's quantum annealer for this project. D-Wave is a company located in Canada. It produces commercial quantum annealers, and they're basically restricted versions of adiabatic quantum computers that are error-prone but can still solve optimization problems. So they're not constructively better than classical algorithms as yet. However, there is a constant factor speed up on certain types of problems. So the types of problems you want to solve on these machines are those problems which are important to be solved in a minimal amount of time. For example, you have to control the traffic signals within 5 or 10 seconds, or else you'll have problems. Some basics about the hardware behind the machines. I already mentioned that adiabatic computers and quantum annealing are two sides of the same coin. Quantum annealing is simply a more restricted version of it. So both function on the principle that you have a cost function and you have to find the minimum of that cost function. And you start from a simple Hamiltonian, evolve to your problem Hamiltonian, and then read out the state of your problem Hamiltonian, and that's the solution to your problem. Adiabatic quantum computing is a universal model of computation. It's polynomially equivalent to the GET model, so it can perform any kind of computation that a theoretical quantum computer could do. But quantum annealing is not, since the error rate is unbound, and as yet you can't perform meaningful error correction. The formalism you use to translate a problem onto this hardware is called the quadratic unconstrained binary optimization. What you do here is you have a quadratic polynomial and you minimize it over a series of binary variables. So for example, you can only have ones and zeros, and you have this little equation here which is basically a condensed form of a quadratic polynomial, and the x vector is a vector of binary variables, x1, x2, x3, all are binary variables, and q is a square matrix of real numbers. So x you have to find, the vector x, and q you are given. Q is basically the definition of the problem. All the information of the problem is condensed into the q matrix q. Now let's have a look at the nitty-gritty of how the backend of the D-Wave hardware works. A bit of overview, not going too much into detail, but the basic steps. First, you obviously have to define your problem. This involves formulating the cost function and the binary variable in question. Then you have when it goes to the D-Wave hardware, it transforms this to an icing problem. The icing problem is equivalent to a QUBO through these transformations. Basically, you transform the -1 and +1 spins into 1, 0, and 1 respectively. And the interaction magnetic fields and the self-interaction fields are transformable and vice versa with the Q matrix as well. So once you've transformed this problem into an icing problem, you have a bit of background on what the hardware actually looks like. It's a map of qubits, a graph of qubits. So each qubit is linked to a few other qubits. In the current generation, I think each qubit was linked to 4 or 5 other qubits, but this number is changing, and the next generation will probably have about up to 15 qubit links per qubit. So you have to map this problem onto the qubit graph. For example, you have a quadratic term in your cost function, for example, x1, x3. To map that quadratic function onto your hardware, you have to map the first qubit onto x1 and the third qubit onto x3 and have a link between them. These links are couplers, and I won't go into too much into the details of the hardware, but that's basically the overview. So you have couplers between qubits, and the qubits represent variables. Then you start from an initial Hamiltonian, which is a simple superposition, and you allow it to settle into its ground state. Then you evolve the system. You evolve the system towards the problem Hamiltonian, that is defined by the Ising problem that came from the QUBO in the first place. And then evolving this over about a few microseconds, typically it's 20 microseconds, but you can increase or decrease the time. If you increase the anneal time, you will end up with better solutions, more closer to the actual minima. But it's a trade-off between speed and solution quality. Once that's done, you read the states of the qubits, and there's a high probability they'll collapse into the solutions to your problem, the ground state. But there's always some element of error and uncertainty, since there is not 100% probability for each qubit to be in its respective required state. So you have to repeat steps 3 to 5 over several times. And then you take the readings which represent the lowest minimum. Now let's move on to the first problem that we talked about earlier, the real-world applications. This was originally work by Volkswagen, but we made some improvements to the parameters of this problem and recreated it ourselves, and ran some instances over several areas and created a general framework for this. So the problem is that we have a map, which is basically a graph with nodes and segments, and we have some cars which are located at different nodes, and each car wants to go to a certain place, some other node. So the problem is that you have to assign routes to cars such that their overlap, their congestion is minimized. The cost function for this problem is this. It looks a bit complicated, but it's pretty simple. The binary variable in question, you have to have a binary variable for each problem. So in this case, it's Qij. Qij represents so the index over cars is I, and the index over routes is j. So if Qij is 1, that means the ith car takes the jth route, and 0 if ith car does not take the jth route. And this is a triple summation over all the cars, all the routes, and then this S from Sj is sort of a selection rule to check for overlap. Since you only want to minimize the overlap of the routes, you have to have this condition so that you can check segment overlap and then minimize accordingly. And of course, you have to sum over all the segments in the map as well. This term takes care of the congestion part. This is a necessary constraint because you can't have multiple variables Qij with the same I and multiple j both being 1, since that represents a pretty weird unphysical solution. So you have to have each car taking only one route. It's not a quantum car, it's a classical car. So that's pretty much it. And so this term, if the quantity inside brackets is 0, which it will only be if only one of the Qij is 1, then this goes to 0, and the system avoids this cost lambda. Lambda is some huge number that the system is going to try and avoid, since it wants a minimum solution. This is a simple example for how to solve this problem. Hasham is going to present this.
Okay. Now that we know a little bit about this cost function, let's just walk through a very simple example to understand all these terms. Over here we have this very simple map with only 5 roads, and we have 2 cars. So one car is over here and the other one is over there. Now both of these cars, they have different sources, but they want to go to the same destination. So this is the destination. So the first thing that we do is that we label our car. So this is the car I equals to 1 and this is the car I equals to 2. So and then J represents the routes for each of the cars. So this car can take this route or it can take this route. So these are the routes for the orange car, and then these are the routes for the gray car. So it can take this route or it can take this route to reach to this destination. Okay, so we first look at the first term of our cost function. This is, let's just call this term Q1. So over here you can see those four graphs. This is our main graph over here, and we have this set S. S constitutes all of the segments. So there you have A, B, C, D, E, F. Now the best way to understand this cost function is to walk through this table. So S, as you can see that there is a sum over S. So S takes the value of A, B, C, D, E, F. So when S is equal to A, what we do is that we write all of those binary variables from Q11 to Q22, and then we look at this graph. So this is the segment A. Then we see that is A present in this graph. So it's not here because this car takes BF. So A is not here. So we cancel this term. Now, yes, A is over here. So we keep this term and then we cancel those two terms as well. So we're left with Q11. And since there is a square, we square this thing. Now let's just go through the last one when S is equal to F. So as you can see that this is F and F is present over here. So we keep the first term. It's not over here. We cancel the second term. F is over here. We keep the third term and then we cancel the last term. So we're left with this. And then in the end, since there is a summation over here, we sum over all of these terms. So we get this and then we open the square by using the binary rule. Binary rule is basically just that if you have Q11 square, this is equal to Q11 because Q11 is a binary variable. It can only take the value of 0 or 1. So 0 square is 0 and 1 square is 1. So when we solve this, just a bit of algebra, then we have this expression. The next thing we do is that we make the so-called Q matrix from this thing. So the way it works is that we have one Q11 over here. So this is Q11, Q11. So we put the coefficients here. This is Q11 and 12. So we put the coefficient over here. Q11 and Q12. And similarly, you can do it for all the other coefficients. Now we have the second term. So this term is basically just the constraint term. It's the sanity check. We don't want one car to take two routes. So this is the constraint term. It constrains one car to only take one route. Similarly, like we did with the last function, we open this thing. We open this summation, and this is a bit of algebra, and then we convert it into our Q2. So this one has this lambda, and this lambda is the penalty. So this penalty has to be greater than the largest number in Q1. So as you can see over here, 4 is the largest number. So we can take it 5, 6, 7, any number greater than 4. Then we add both of those Q1 and Q2, and we get this matrix. Now we have to solve this matrix. So it can, since this is really a small matrix, just 4 by 4 matrix, we can solve this by using the hit and try rule, by just putting the different values and seeing that which choices of Q11 and Q12 and all these gives us the minimum result. But so yeah, we can just solve it, and this is the solution that we get. So it's 1, 0, 0, 1. The way we interpret this thing is that since there is a 1 here, so Q11, we choose this path. This thing is Q12, it's 0, so we cancel this path, we cancel this one, and we keep this one. Now, a couple of things here to notice. First thing, that every car is taking only one route. So this is the function of this constraint. And then you can see that the congestion is minimized in a way that there is no overlap between these two paths. So this one takes this path and this car takes this path. So there is no overlap. So in a sense, congestion is minimized. But this is a very simple example with only 2 cars. Now, if you have multiple cars and you have a really big map, so this thing doesn't work. So what we have to do is that we made the Python code. So it does is that it just go through all of the cars and on every road segment and makes the cost function for you. So the first thing is that we take the map of a map of ours, just a map, and then the second thing that we input into the program is the source and destination of the cars. So this is for ith car, and we run I from 1 to n. So n is the total number of cars. Then the program, it uses a couple of algorithms, the Dijkstra algorithm, which is the algorithm to find the shortest path between the 2 points, and then the Jens algorithm to find the other paths in order of increasing length. Then we give all of this result to something called Jaccard similarity index. What it does is that it tries to only choose those paths that are in a way dissimilar from each other. So we get these paths and then we loop over all the cars. So we keep doing this until we're done with every car. Then we get the cube matrix. So that was the matrix that we have before, the 2 by 2 matrix, but it can get like 100 by 100 or even larger than that. Then we solve this cube matrix using, so this part is a part that is really, that is a quantum that is solved on the quantum computer. So we solve this and then we get the result just like that 1011, and then we interpret the result to see what the results means. So we made this graphical user interface to just have fun and run multiple examples. So here we put in the number of cars, the routes that are proposed for each car. In the example before, we only did for each car we have 2 routes, and then from those 2 routes we choose the best route. So you can take this number to 3, 4, 5, 6, and the solution will keep getting better. Then over here you can choose the location of the map. We have some locations set already. So this thing is that you tell the program that you want the cars to start at the same point and end at the same point or not. And this is the method of computation. So you can solve it classically, or you can solve it using a quantum linear. You can send your problem to a quantum computer that's sitting in Canada, and it can send the result back to you. So we can try to still running. Okay, we can try to run a problem instant on that quantum computer, but let's see if it works. In the meantime, let's understand what the results are. So over here, you can see that if every driver tries to take the shortest path, so let's just say that we have some number of cars that are over here and they want to come to this point. So if every driver blindly takes the shortest path, so you can have a lot of congestion on this road. But if this program gives the routes to those drivers, you can see that the traffic can get spread out. So there is a lot less congestion. So this is the comparison. And in this test example, we have the same source, but we have the different destinations. So still you can see in this thing, it's still better. There is a lot more roads that are being used that weren't used over here. So this is the interpretation of the result. Let's see if it, okay, it's taking some time. All right, so let's discuss about the second problem that we formulated and solved. So we formulated and solved this problem ourselves. So this is the problem statement. Basically, you're given a map with intersections, and at every intersection you have traffic signals. So the challenge is to find the right mode on each of the intersections such that the traffic is optimized. So let's see, this is the map. So here we have 9 intersections, and at every intersection you have a signal, traffic signal, and you have to control the signal in such a way that the traffic is optimized. And these are the controls that you have. You can choose traffic to go like this or that, and all of those 6 modes. So let's define our indices. So I over here represents the intersection. So you can label intersection with I equals to 1, 2, 3, and 4. And J is the mode number. So you can have mode 1 to 6. Now, let's define a binary variable. Our binary variable is xij. Since it's binary, it can take only 1 and 0. So if this variable has a value 1, it means that on the ith intersection, jth mode is active. Otherwise, it's 0 if that mode is not active. Some other mode is active. So let's discuss the cost function of this problem. So we have, this is the term that we call local optimization term. So what it does is that it tries to optimize the traffic on every intersection. So the purpose of this thing is, of this cost function is to clear the largest number of cars at every intersection. So if you have, here you have an intersection. So what it does is that it tries to find the mode that clears the maximum number of cars right here. It doesn't care about what's happening here or here. So it's sort of like local optimization term. So let's understand this term. So we know that xij here are the binary variables. We know what I is, what j is, and lambda is just a weight factor. So let's see what these Cij are. So Cij are defined like this. So let's first understand this thing A. So I represents the intersection. So on every intersection there is AI1. So AI1 represents the number of cars that are over here, north side of the road. Similarly, AI2 are the cars over here, and AI3 cars here, and AI4 cars here. So Ci1 basically represents that if we turn the mode 1 on, so remember mode 1 is this mode. So if we turn this mode on, how many cars can we get cleared? So as you know that if we have some number of cars over here, not every car wants to go straight down. Some of them would want to go to the right and some to the left. So we define this fraction fi1 that when we multiply it with ai1, when it gives us the amount of cars that wants to go down the road. So similarly, we have fi2 ai1 that when we multiply fi2, this fraction with this, we get the amount of cars that wants to go up the road. So Ci1 basically is the amount of cars that will get cleared if mode 1 is active at this intersection. Similarly, AI2 is the amount of cars that will get cleared if mode 2 is activated. So we have these terms. So mode I4 is that many cars that will get cleared, and this is I4 and CI5 and CI6. For example, if this is the intersection and you have one car here and two cars there, so the best mode to activate is this mode. This is I think the third mode on if j is equal to 3 here. And in this case, if you have only a couple of cars there, then this mode is the best mode. So this Q1 basically tries to find the right mode that will clear out the maximum number of cars. Now let's look at the second term in our cost function. This is the second term. It's the global optimization term. So the goal of this term is to try to have the cars in such a way that when they pass one intersection, they will, by the time they will reach the next intersection, the light over there would probably be green. So they don't have to stop, the flow of the traffic is maintained. So this is the purpose of this cost function. Let's go through this. This is the syncing that I was talking about. So basically, you have a car that starts from here. By the time it reaches close to the signal will turn green, so it doesn't have to stop, ideally. Now, if you look back here at this cost function, let's just first understand what these indices are, A dash and A, B dash and B, and these indices. So to understand this, we have this table. So basically what this table does is that on this column we have the modes arranged. So we have mode 1, 2, 3, 4, 5, 6. And here we have basically the dashed indices are the indices that are the intersections that are affected if this mode is turned on. So remember, J is the mode where cars goes up and down. So that's why we have this up and down over here. And this is the ideal mode that we want on the up intersection to turn on, so that the traffic is optimized, the flow is optimized. So similarly, we can turn on the intersection above our intersection, we can have mode 1 or mode 2. But if we had turned the mode 2 on, it will give us the more bonus, the more syncing will happen. So we shaded these regions. So similarly, we have made this table for all the intersections. These are just the values that goes over here when we open the term, when we just expand these terms. Now, there's another issue. As you can see in this animation, that when the car starts from here, we don't want this signal to turn on green instantaneously. We want to wait so that if this car we close enough to the signal, so that it will turn green. So this is a function of this tau I dash. We don't want instantaneous syncing. So I dash are just the intersection. I is the intersection of focus, and I dash is the next intersection after that. So it's most of the time it's 0. It'll only turn 1 when the car is close enough to that intersection. And then lastly, we have the constraint term. This is just like the last case. We want to make sure that on every intersection there is only one mode that's on at any time. So this is the function of this constraint term. And now we add all of these terms together, and this is our cost function for the second problem. So as before, we wrote the Python code for this. So this code takes in the speed limit of, it basically takes in the graph. So it knows the speed limit of each segment. It knows the just the map, and it also understands the traffic density. So then we feed all of these things into our code, and we get the Q matrix. And then we can solve this Q matrix on the D-Wave hardware, or we can simulate that quantum annealing on our PC. And then we interpret the result, and then we run the traffic simulation, and we keep looping. This traffic keeps changing, and we keep going through this program. So these are the results. So right now, traffic is being controlled by what's called the fixed signal cycle. So what they do is that they just fix the cycle that 15 seconds or 30 seconds you have this mode on, and then the next 30 seconds you have this mode on, and so forth. So if you use this system, we ran this test on 36 intersections, so 36 signals, and we have about 4,000 cars on those 36 intersections. So for every 5 minutes, you have 105 hours that's wasted just standing waiting for your light to turn green. So if we use this dynamic optimized cycle that we developed, you can bring down the time to 50 hours. So you can basically save about 50 hours. And this is just the minimum amount of time minimum bonus that you can get. You can actually improve it to all the way to here if you know everything about the traffic and where every car is. So now, here is this thing so the big question, is D-Wave useful? Well, not now. Right now, the best classical algorithms, D-Wave can compete with those algorithms. So D-Wave have their own algorithm called QB-solve. So QB-solve classically outperforms the quantum version. But as you can see over here, that there is a constant improvement, just like we know Moore's law in classical computing, there is the Rose's law in quantum computing. So D-Wave has their own Moore's law. So they keep on improving the number of qubits for every number of years. So if this trend keeps on going, so one day we will for sure have the quantum computers that are faster than the classical computers. So thank you. Let's see if we have. Okay, so we finally get the results. So as you can see, this is just like the last results, but we ran them on a different area. This is blue area based in Islamabad. So we ran it over here. So you can maybe see that this is when we don't turn on the optimization. So it's mostly red, but when we use the optimization, so you can see that some of the roads are green, so there is less congestion. Thank you.